Imagine a universe where the secrets of distant planets are finally unlocked, where we can peer into worlds covered not by oceans, but by endless layers of steam. This isn't science fiction. It's the cutting-edge focus of new research aiming to decode steam worlds, orbiting stars far beyond our solar system. These mysterious celestial bodies hold clues about the diversity of planetary systems and could reshape how we think about habitability in the cosmos. But here's where things get even more intriguing. What if these steamy realms, despite being too hot for life as we know it, still teach us something profound about the universe? Astrobiologists often compare the search for extraterrestrial life to scanning a vast desert. Essentially, you look for signs of water, which is widely regarded as a key ingredient for life. Among the many types of exoplanets discovered so far, one category stands out due to its prevalence and peculiar characteristics: sub-Neptunes. These planets fall between Earth and Neptune in terms of size and mass, suggesting they might harbor significant amounts of water within their interiors. However, there's a catch. Unlike Earth, sub-Neptunes typically orbit much closer to their host stars, making them far too scorching to sustain liquid water on their surfaces. Instead, their environments consist of thick atmospheres filled with steam, layered atop exotic phases of water that defy conventional definitions of gas or liquid. The concept of steam worlds has fascinated scientists ever since predictions about their existence emerged 2 decades ago. Yet, understanding exactly what these planets are made of and how they came to be has remained elusive until now. A team of researchers at the University of California, Santa Cruz, has developed an advanced modeling technique designed to shed light on the composition and evolutionary history of these enigmatic planets. According to Artem Agachin, the postdoctoral researcher who spearheaded this effort, when we grasp how the most frequently observed planets in the universe form, we can redirect our attention to rarer exoplanets that may actually support life. Published in the Astrophysical Journal on July 24th, this groundbreaking study was co-authored by esteemed figures in the field, including Professor Natalie Batalla, head of UC Santa Cruz's Astrobiology Initiative, and Professor Jonathan Fortney, chair of the university's Astronomy and Astrophysics Department. Their work represents a leap forward in interpreting data collected by powerful telescopes like the James Webb Space Telescope, JWST, which recently confirmed the presence of steam on a number of sub-Neptunes. With JWST expected to discover dozens more of these planets, having accurate models becomes crucial for connecting surface observations to internal structures. Historically, models used to characterize sub-Neptunes were adapted from studies of icy moons within our own solar system, such as Europa and Enceladus. While these moons feature layered compositions, icy crusts floating above subsurface oceans, the sub-Neptunes differ drastically. They are significantly more massive, ranging from 10 to 100 times the mass of Earth, and experience extreme temperatures and pressures due to their proximity to their host stars. Under immense pressure and heat, water molecules undergo dramatic transformations, sometimes forming what's known as superionic ice. In this exotic phase, hydrogen ions flow freely through a rigid lattice of oxygen atoms, a phenomenon thought to exist in the interiors of planets like Uranus and Neptune, as well as potentially in sub-Neptunes. Understanding these complex behaviors is no small feat. To create their model, the UC Santa Cruz team incorporated experimental findings on how water behaves under extreme conditions, advancing theoretical frameworks needed to simulate these processes accurately. Planetary interiors act as natural laboratories for exploring scenarios that are nearly impossible to replicate on Earth, explained Batalla. What we learn from studying these water worlds could lead to applications we haven't yet imagined. Perhaps some of these planets represent entirely new niches for life in the galaxy. But the implications of this research extend beyond just identifying potential habitats. By modeling the distribution of water in sub-Neptunes, scientists gain insights into how this vital molecule moves and interacts during the formation of planetary systems. Water, after all, possesses remarkable qualities that make it central to discussions about complexity and life itself. For instance, it acts as both an acid and a base, playing a pivotal role in chemical equilibria. Its ability to dissolve salts, sugars, and amino acids makes it indispensable for biological processes. Hydrogen bonding gives water unusual properties such as high viscosity, elevated boiling points, and exceptional thermal storage capabilities. Life can be seen as a manifestation of complexity, Aguashin noted, and water's diverse attributes enable that complexity to flourish. Another critical aspect of the team's approach is its emphasis on the dynamic evolution of sub-Neptunes over millions or billions of years. Planetary properties aren't static. They change dramatically over time. Accounting for this evolution is essential for creating reliable models, according to Aguashin. These models will face real-world tests thanks to ongoing observations with JWST and upcoming missions like the European Space Agency's PLATO telescope, set to launch in the near future. Designed to detect Earth-like planets in habitable zones around their stars, PLATO will provide valuable feedback on the accuracy of current models. PLATO will help us refine our predictions and guide the next steps in the quest to find life beyond Earth, Aguashin added. So while the search continues, one thing is clear. These STEAM worlds are more than just cosmic curiosities. They're windows into the fundamental workings of the universe. And this is the part most people miss. Could these seemingly inhospitable planets harbor forms of life radically different from anything we've imagined? Or do they serve as stepping stones toward discovering truly habitable worlds? Share your thoughts in the comments below.